We can define chemistry as the study of matter and its properties, changes in matter, and the energy associated with these changes. Okay, and so right now we're going to talk about the energy associated with those changes, and that is the study of thermochemistry. Thermochemistry is the study of energy changes when chemical reactions occur. And when we do this, we define two locations. We define a system, which is an area of concern, and that might be a reaction is one example of a system. And then everything else in the entire universe is the surroundings. Okay, and so then we talk about the energy of the system, and again, whatever we're concerned about, and we'll define that as E, the energy of the system. And we define energy transferred to and from the system as heat and work. And heat we label as Q, small case q, and work we label as large case W. Okay, and because of those labels, we can say the change in energy, delta E, for a system, I'll get rid of that stray mark, okay, start over. Delta E for a system is equal to the heat plus the work. So that's an important equation to remember about the change in energy of the system. All right, and so we have to define signs for the system. Okay, so this is change in energy. And it's equal to Q, and Q plus W. And Q is positive, we define it as being positive when the system takes in heat. And so conversely, we define it as negative when the system loses heat. All right, and for work, we will define that as positive when work is done on the system. And we'll define it as negative when work is done by the system. Okay, and we'll show some examples of these, but the change in energy of the system will go up if the system takes in heat, and the energy will go up if work is done on the system. So let's do a couple of examples. We'll do simple systems. First one we'll do is a cup of coffee poured and sitting out on a table, and the coffee is hot. Okay, so we define coffee as our system, and then the surroundings is everything else. It includes the cup, it includes the air in the room, it includes the table, and it includes everything else other than the coffee itself. So since this coffee is losing heat, then that means Q is negative. We said up here that when the system loses heat, Q is negative. So Q is negative, loses heat. So during this process, delta E, which equals Q plus W, and we're only concerned about Q at this point, since Q loses heat, then delta E is also negative. So the change in energy is negative, and energy goes down for that system. Let's look at a different example of a system. Let's say we have a carbonated beverage, and we put a balloon over the top of the container, and in time, let's say that the carbonated beverage loses its carbonation, and so it gives off gas, and it is able to blow up a balloon. Okay, then we would say that this beverage, Coke, is the system, including the dissolved gas to start, and as the gas comes out of solution, it blows up the balloon, and the surroundings will include the balloon and the air in the room and everything else in the room. Okay, so when the system loses carbon dioxide, it will blow up the balloon. Dissolved carbon dioxide. Okay, so what happened? Work was done by the system. The system was the beverage, and it did work. It blew up the balloon. Okay, so it does work. The system does work. Which means that work is negative, okay, because we defined work as being negative when the system does work. Work was positive when work is done on the system. But this system did work, so delta E in this case is negative. All right, and we can talk about the first law of thermodynamics, which tells us that energy is conserved. And by this we mean total energy. So if the energy, so therefore the energy, whatever the change in energy is for the system, it's got to be equal and opposite to the change in energy for the surroundings. So if our system lost energy, then the surroundings gained it. If our system gained energy, the surroundings lost it. Because energy will always be conserved. All right, and energy is given in units, usually of a joule for this course. SI, it's an SI-derived unit. Okay, so it's we write it as a joule, and whatever number of joules, 1 joule with a capital J, and that 1 joule is equal to 1 kilogram meter squared per second squared. So there's your SI units, and the joule is derived from that. Sometimes we also talk about a calorie, and a calorie is abbreviated CAL, and that is related to a joule through this equation. 4.184 joules is equal to a calorie. But usually we will use joules. And we can talk about state functions, whether something is a state function or not. State functions are variables that depend on the initial state and the final state only. They don't care about the path. They don't care about, they're not affected by how you got from the final state, from the initial state to the final state, just where you were in the beginning and where you were in the end. Okay, so examples of stated functions are anything that use deltas in front of them. Okay, if they use deltas, then it's a state function. So examples are energy, which we just did, change in energy, pressure, volume, temperature, all those things use deltas in front of them and only depend on initial and final state. Q and W, however, are not state functions. Okay, they are not state functions. They do depend on the path. Okay, so what are some other examples of things that depend on path? Let me give you an example of a person and a very tall building. Okay, now, if that person can go to the top of the building, okay, so there's an elevation change, okay, and it doesn't matter how this person gets there, whether they fly in a balloon and go over to the top of the building, or whether they go to the bottom of the building and climb up, or whether they run all the way around the world and come back and then go up the building. It doesn't depend on their path. The elevation change from the ground to the top does not depend on the path. Okay, so elevation change is a state function. However, the distance from where the person is to the top will depend on their path. Okay, they can go straight there, they can go to the bottom floor and go up the elevator, they can go all the way around the earth and to the top, and those distances will all be different. And they're still got the same initial place and the same final place, so distance is not a state function. So there's an example of things that, one thing that does depend on path and one thing that does not depend on path. All right, so here's something for you to try. Find the change in internal energy, which is energy of the system, delta E, for a process that absorbs 34.5 kilojoules of heat and performs 250.9 joules of work on the surroundings. Okay, stop the tape and calculate that. We will use delta E equals Q plus W. Okay, so Q is heat. And remember that heat is defined as what the system takes in. Okay, so the system does absorb heat. So the word absorbs tells you that Q is positive. Okay, so we have 34.5 kilojoules for heat. It's positive. Now the work term, work is defined as positive when work is done on the system. But in this case, the system is performing work on the surroundings. So the system is not, the work is going to be negative. So we're going to need to put a negative on this number. Okay, so we'll do minus 250.9 joules. And notice we have kilojoules and joules, so in order to add them up, we have to convert one of them. So we will make it negative 0.2509 joules, and then when we add them up, the answer is 34.2 kilojoules. Whoops, that became kilojoules. All right, so let's focus on the work term for a minute here. We talked about work in terms of a gas blowing up a balloon. Okay, but there are a couple kinds of work associated with chemical reactions. The two main ones are electrical work, and we are not going to focus on that at this point. The one we are going to focus on is what we're going to call PV work, which is exactly like the balloon blowing up. It's expanding and contracting gases. Okay, so anytime we have a change in moles of gases, we will have PV work. And work is then equal to minus P times delta V, and that is true for constant pressure. And most of the time we will be working with constant pressure because we're working in an open room where the pressure is atmospheric pressure. All right, so we have our equation that the work term is equal to, for everything we're going to consider at this point, work is equal to minus P delta V. All right, so what can we do with that? We notice we have a delta V in there. So let's look at some examples of chemical reactions and how that term comes out. So if delta V is about 0, if there's no significant change in volume, then the work term is essentially 0, so we can ignore it. Okay, what are examples of that? Here's a reaction that has aqueous solutions making a solid and aqueous solutions, a precipitation reaction, and there's no moles of gases involved at all. So this is one in which the change in volume is going to be insignificant. Okay, the only time volume is significant, the change in volume is significant, is when you have gases produced or consumed. So this one is not going to have a significant work term. The second reaction does have gases. You have nitrogen and oxygen forming NO gas, but there's 2 moles to start, 1 in nitrogen, 1 in oxygen, and you make 2 moles of gas. So the change in volume is essentially 0. You have 2 moles of gases making 2 moles of gases, so the gas amounts are unchanged when you react this. So those are 2 where the work term is insignificant. Now let's look at reactions where the moles of gas do change. Okay, here delta V is not equal to 0, so the work term does matter. Okay, so both of these have changes in gas amounts. So first you have 2 moles of hydrogen and 1 mole of oxygen going to 2 moles of water. So you're decreasing the moles of gas, which means your change in volume is going to be negative, right? Change in volume is final volume minus initial volume, It'll get smaller, it's negative. And if delta V is negative, remember W equals minus P delta V. So if delta V is negative, then the work term is going to be positive because of the negative in the equation. Here's another example. You have a solid and aqueous solution producing aqueous solution and a gas. So it's bubbling. In this case, you're producing gas, so you have an increase in volume. Delta V is positive, which means your work term is going to be negative because of the negative there. So you can predict the sign of those. Okay, well, how big is this work term? How significant is it? You may have noticed from the example I already did that Q was given in kilojoules, whereas W, the work term, was only given in joules, and this is typical. Q is usually much larger than W. So essentially, remember that delta E equals Q plus W, so if Q is much larger than W, then delta E is fairly close to just equaling Q. It's not exact, and we just talked about cases where work is important and where it's not. So when the number of moles of gases change, then work is more significant, but it's still very small. So we often just ignore the work term altogether. Work is often ignored. Sometimes it's essentially zero, other times it's just ignored because it's small. Okay, and further, if you are at constant pressure, which we often are, we can also say that Q is that point a state function. Whenever pressure is constant, Q is then a state function, and we're going to define that state function as enthalpy. H is enthalpy. So Q is going to equal delta H. We now put a delta on it because it's a state function. And this is defining a state function. Known as enthalpy. All right, so since Q at constant pressure is delta H and Q is approximately delta E, that means that delta E is approximately equal to delta H. And this is true at constant pressure, which we often are working at. Okay, so we're going to ignore the work term often. There are times when we'll be asked to calculate a work term, but most of the time we're going to ignore it. But just to look a little more at work, let's have you try a problem where you look at these four reactions, decide for which reaction or reactions, the work term would be positive. So give that a try. Okay, so what makes the work term positive? The work term will be, remember the work term is negative P delta V. So the work term will be positive when delta V is negative. Alright, so first let's see which ones even have a significant work term at all. The first reaction has liquids, aqueous, solid, aqueous. The work term is essentially 0. The second one has gases, the third one has gases. This one has 2 moles going to 1 mole. Okay, so that's a decrease in the moles of gas, so that would be a delta V that is negative. And that's exactly what we're looking for. So this is the one where the work term will be positive. Let's look at the others. Here we have a solid and a gas going to 2 moles of gas. So you have an increase in the moles of gas. Delta V will be positive, which means the work is negative. That's not what we want. And finally, you have 3 moles of gas in reactants, 1 plus 2, making 3 moles of gas in the products. So delta V is essentially 0, and work is essentially 0.